Find a seat if you can, and we're going to get started now. My name is John Lynn. I'm the scientific director of the Wilkes Center for Climate Science and Policy. And I can't tell you how excited I am to welcome all of you to the first seminar in our brand new building, our brand new space. We're a brand new beautiful room. And when I thought about what our first seminar should be, I thought, well, you've got to invite someone from this building. And you pick up on no better person than Bromley, who has given a talk in atmospheric science before on lunar dust, which I thought was just fascinating, perfect topic for a seminar. So Professor Bromley is a professor in the Department of Physics and Astronomy, former chair of the department, and he's a theoretical computational astrophysicist. His work spans a range of topics, including astrophysical cosmology, large-scale structure of the universe, relativistics, astrophysics, with a focus on supermassive black holes, and planet formation, the ultimate goal of understanding the possibility for life on distant planets and life on Earth. Recent highlights include the search for Planet 9, which is a hypothetical super-Earth on the regions of our solar system, and a study to assess whether dusty grains launched into space could be used as a solar shield to prevent catastrophic changes at Earth's climate. So that's today's topic. Much of this work involves calculations performed by NASA supercomputers. Throughout, Ben has been committed to sharing his love of astrophysics and the research strategies he uses with students here at the University of Utah. So please join me in welcoming Bromley.
Everyone, thank you for being here. This is really good to see you all. I will be giving you a talk today on dust as a solar shield. And I wanted to start off with kind of a short form summary for what we'll be going through today. The context is continued, indeed accelerating warming of Earth's climate. The Wilkes Center, and I'm really grateful to be here as invited by the center, is focused on practical solutions to climate change. And in this talk, I will be discussing space-based mitigation strategies, okay? And collision with the word practical. Now, we're all here because we really care about our planet and our future here on our planet. And it is my deep hope that the ideas that I convey to you will lead you to say something like the following, and I hope I get the intonation correct. Cool story, then. Okay, here's an overview of how I will roll this talk out. I'll talk first about dust. I'll talk second about orbits. And third, I'll talk about a solar shield. So here we go. I did want to give a sense of what I do because it's part of the story for the subject of today's talk. I work in a variety of areas, as mentioned, but I spend a lot of time on planet formation, both within the solar system and outside the solar system. And these images are just snapshots from work that I've done. The images on the upper right, this is Pluto, and that's an exoplanetary system that's forming, and you can see rings of dust around it. So I've spent a good amount of time studying astrophysical dust. I did want to give you this slide of some recent work because it highlights an element of my research, which is that it's heavily computational often. And this is a simulation of the universe on very, very large scales. Dots here, pixels here, are multiple galaxies in scale. This shows the large scale structure forming, and it starts off kind of blurry and ends up in a much more defined and concrete view of the universe as the universe evolves to the present day. I like to think of our faculty meetings in physics and astronomy in this way as well. I really like our faculty meetings, and they start off kind of blurry, and then they end up being crystal clear. First, dust. This is an image of the Sombrero Galaxy. And you can see this outer ring of dust that obscures the starlight. Dust basically is everywhere. When I refer to dust, I'm going to be referring to something specific, but the generic view of dust is reasonable. These snapshots show different sort of realizations of dust or how dust is manifested in our physical world. I love the dust bunnies picture. Their dust bunnies are certainly a part of my own living environment. Their formation through electrostatic forces is actually something that may be important for the growth of planets from dust around host stars. Speaking of which, these are images that show dusty rings around nearby stars. The central star feature has been blotted out in the majority of these images. And what you see surrounding these stars is dust. And this dust is either representative of material that's forming planets or material that is being produced as planets form. And that's what I've worked on for a big chunk of my career here. So what is space? When we look at dust in space and we talk about dust, we're really talking about tiny particles, things that are sort of micron size. And just, for comparison, human hair is roughly 50 microns in diameter, and the dust, unlike human hair, is made of silicates or ices. The origin of dust is either condensation as part of the chemistry of interstellar intergalactic space, and also collisions. One property that dust has that's important for this talk is that it's got a very large surface area to mass. And this is an example that I give you, but this was actually a thought that kind of led to this whole effort that I'll talk about today, is thinking about the moon and how bright the moon is and the surface area that the moon has to intercept starlight. And I put some numbers here for you. The sort of the surface area of the moon, if you will, is roughly the area of the United States in square miles or square kilometers. If we were to take the moon and break it up into micron-sized dust grains, just shred it, the surface area of the moon would become trillions of times this area. Indeed, if you think about the surface area of a sphere painted at the orbital distance of the Earth, an astronomical unit, around the sun, and put a moon's worth of dust on that sphere, you would completely blot out the sun 50 times over. So dust is incredibly powerful as something that can intercept starlight. And even a small amount of dust for the moon is a tiny, tiny fraction of the mass of our host star. So typically when we go out and we look at observational objects, when we look for objects around stars, what we see first, if there's dust there, we'll see it most brightly. To give you like one graphic for how this all works, imagine you had a can of spray paint. The can of spray paint is not super visible. Like if I'm thinking of being on the subway in some of my favorite cities back east, if I see a can of spray paint, I'm not going to be seeing it very well. But if you break up the contents of the can of spray paint, you can see it quite effectively. So that's the main idea. Okay, the purpose of this slide in a scale of purposefulness as well. So let me just describe what I'm the main message. When we study dust in space, we can do so through a combination of quantitative tools, laboratory experiments, and observations of dust to understand its properties. Some of the things that are important are the physical characteristics of dust, how dust interacts with light, depending on light's color or wavelength. Depends on the structure of the dust, if it's a solid sphere, or if it's very irregular, or possibly even fluffy or porous, I think snowflakes in this case. We have the tools, astronomers are excellent at their interpretation of measurements of dust. Okay, now I'm going to be thinking about dust around stars because that's kind of where I am used to seeing dust. The dust orbits stars just like other things, like planets. It feels a gravitational force and can orbit in a manner of planets, but dust is actually really small. And it turns out that the light of a star can be intense enough to push that dust particle around through a phenomenon which we call radiation pressure. So the dust will feel pressure from the starlight and get pushed around. It's possible also that wind from a host star can physically push dust around in the manner that you would intuitively sense. So one of the takeaways of this slide is that dust doesn't tend to linger, especially if it's very small, around the host star. It typically can't just sit in orbit like a planet. It will get blown away. As an aside, okay, I do planet formation, so I'm going to talk a little bit about that. What does dust do when it's around a young star? This image on the left is a young star surrounded by a gaseous disk that's very rich in dust particles. Through a process of collision, possibly even gas dynamics and turbulence, the small dust grains, which are actually observed in new stellar systems, are glommed together. They coagulate in some manner or another, and they collide with each other and they stick together. Collisions drive mergers, and over time scales of millions of years, we start off with a system of many small bodies that get hierarchically chunked together to become a very few large ones. Okay, so the process is a little bit competitive. I didn't want to give you the sense of this nice regular growth. I'm about to give you the most overused slide I have on this campus. So I love this reminder of how the process actually plays out in the competitive growth of planets as they gather up material from their surroundings. So this simulation will show you how these small bodies, in the presence of a competitively growing larger one, become a bigger planet. There you go. I think I made this with technology in 1998. It hasn't changed. So the takeaway from this slide is to the dust bunny, the hat shall be given. The largest of the dust bunnies are able to acquire much more mass and more rapidly than others around them. And that sort of gives you a sense of how planet formation takes place in practice. The dust that we can see, that I've been talking about, actually starts off quite plentifully in young systems. You see that cloud of dust-rich gas on the left. But as planets grow, the dust becomes more and more scarce. The dust gets swept up in growing bodies, becomes part of growing bodies themselves, and we don't see much dust around stars of sort of millions or tens of millions of years old. But it turns out as larger bodies form, giant collisions between bodies can produce vast quantities of dust, and we actually can see the result of those collisions. I focus in on this particular object, the well-known star Omaha. It has a debris disk. This image is from GWST, the beautiful space telescope recently launched by NASA. The star is a heavy one. It's larger than our sun. The ring that you see on the outermost part of this image is basically about 2 lunar masses worth of dust. And we can see that around the star. If there was an object that were 2 lunar masses, we wouldn't see it at all. And because of the things that I talked about in terms of the forces that dust grains feel that are different from gravity that cause the dust to leave the system, when we see a ring like this, it has to be recent or recently replenished. So when we see rings of dust, we are seeing signals of ongoing planet formation, which is kind of neat. Another place where collisions are important, and I'll just come back to this in a little bit, is on the moon. Our moon orbits the Earth and has no atmosphere to protect it, so it is subject to impacts from small bodies, chunks of asteroids and whatnot. And over billions of years, the surface of the moon has been hit so many times that micron-sized or sub-micron-sized dust has formed and is on the moon's outer layer, known as the regolith. It's a really fine powder pulverized over the eons that our moon has been partnered with us. Part 2, orbital dynamics. I made this picture for you all for this talk. It is stars, some good fraction of the mass of the sun. I put a lot of them together in a volume comparable to the solar system. I've talked about faculty meetings in physics and astronomy. I will dare to venture that other faculty meetings may not have the same flow that ours do of buzz coming into clarity, but maybe better represented. Okay, I'm just going to put out there some brief sort of statements about orbital dynamics about our sun. So this diagram just shows a body, say Earth, on a circular orbit around a star, our sun. It's going with some speed v, just chunking along at uniform speed around the star. Closer in, other bodies will orbit the star, but because of the stronger gravity there, they will be orbiting with a faster speed. Okay, so interior to, say, Earth here, things move more quickly, and outside, it turns out they move more slowly. Okay? It's possible, under some circumstances, to kind of change the speed at which things orbit a star, and we'll take advantage of that in a moment. For example, one way to change the speed, which effectively means changing the mass or the force of gravity felt from the central star, is to have a shepherd planet. So let's think of the Earth as a planetary shepherd that can kind of change the orbital path of things nearby it. This graphic, sorry, it's getting a little bit more confusing, kind of illustrates this fact. Suppose we have Earth here at its orbital distance, 1 astronomical unit. Because of the Earth's gravity, it can kind of weaken the force that a particle inward of it feels from the sun. And for particles beyond Earth, it can kind of contribute to a gravitational force to kind of pull particles along with it. So there are 2 special points known as Lagrange points that are in line with Earth and Sun, where the forces match up just right so that objects at these points orbit right along with the Earth. So the key thing for us is that an object at this L1 point will remain throughout the Earth's orbit exactly between Earth and Sun. This just zooms in a little bit on the L1 Lagrange point, the point in between Earth and Sun. It's at roughly 1.5 million kilometers, a million miles roughly, from Earth. And contrast that with about 150 million kilometers from between Earth and Sun. Objects exactly at L1 stay between Earth and Sun long term. But this is not a stable point. Small perturbations can cause objects at the L1 point to drift rapidly away. When I'm headed down a road where I'm going to be talking to you about putting dust between Earth and Sun, and you can imagine that dust feels the radiation pressure that I mentioned, possibly the solar wind, so that dust will have trouble staying at exactly this point, and that will come to us in a little bit. So just as a reminder that this is serious physics, the James Webb Space Telescope at the L2 point beyond Earth is also in the situation of being in an orbit that it's not stable. It's not going to naturally stay at the location where we want it. It needs to be corrected every so often. And foreshadowing something that I want to mention briefly today, there are other places to put things. We don't need to limit ourselves in considering orbits of dust. It turns out to orbits that are between the Sun and Earth, and I'll talk about that in a little bit. Yeah, so there's a lot of rich dynamics for satellites around Earth, and yeah, I'll get there. So the takeaways from the first two parts, dust is plentiful. It definitely intercepts a lot of starlight per unit mass. And there are special orbits that lie between a planet and its host star. Radiation wind is important to the dynamics in the ultimate orbits that dust particles experience. Okay, and now this is the last part of my talk, the solar shield. Underscoring the importance of the work done in the mission of the Wilkes Center for Planet Science and Policy, I just put these links and these statements. The cause of climate change is greenhouse gas emission that traps the sun's energy. And our practices in terms of managing greenhouse gases must change to secure a livable future. So there are really fascinating, powerful, and important mitigation strategies. In the top two items particularly, one is to leave carbon in the ground. Another may be to determine ways in which carbon can be removed or sequestered from our atmosphere. The third topic, which I will cover today, is solar engineering. And here's what I mean by that. The sun's radiation is a source of heat and energy for our Earth. Were we able to reduce the amount of sunlight that Earth receives, we may be able to cool our planet despite the accelerating climate change that we're experiencing now. People have had interesting ideas. I list them without judgment. Increased reflectivity in clouds, ground level albedo modification, how much sunlight is reflected at the level of the surface of Earth. And atmospheric aerosol injection has been proposed. Blocking sunlight in space is another idea and the focus of what I'll talk about for the remainder of this presentation. The space-based solar shields is actually a really old idea. It's been around for decades. People first when they recognized that climate change could be a threat to life on Earth, began proposing various configurations of things, often at L1, the Lagrange point just mentioned. Solid shields is one idea that has been proposed. Someone talked about moving an asteroid to the L1 point. There's a famous paper on launching a fleet of space umbrellas that are controllable. This image that I have in the upper left is a recent idea from MIT's Media Lab of using space bubbles, material that bubble in the structure, very lightweight and able to deflect starlight from our Earth. Tethered shield from an asteroid is another idea. All of these things involve launching billions of kilograms into space. The basic goal of a solar shield that's space-based is to reduce the solar irradiance by about 1.5% or 2%. This must be sustained over years or decades. And the goal is to minimize environmental impact on Earth. That's why people propose putting it into space as opposed to trying to modify something within our atmosphere, for example. This is not easy. If you think about what you have to do, if you had a solid shield at L1, you need a disk of radius 900 kilometers, roughly the size of the US. So we're talking moving that material, 1 million miles. And if you thought that capturing an asteroid is easy, you need a fortuitous encounter. You also need to essentially subject it to megatons worth of energy to slow it down and gently bring it into whatever orbit you wish. So this is all a challenge. Okay, toward coming to the idea that I'm about to go into more detail, I'm wondering if there are lessons from Earth history that can help us understand solar radiation management. Volcanic activity has been used as a justification for aerosols in the Earth's atmosphere to modify the sunlight that reaches the surface. Major asteroid impacts has similar operation. Solar activity, although probably not responsible for modern minimum, which was a cooling of Earth at the turn of the 17th century, is thing that I began to think about when I first started this project. But basically, I'm here to show you that I was in Shelburne, Vermont during the total eclipse of the sun in 2024. And one really interesting feature about that experience, I wasn't just focused on the actual eclipse because I had one of my kids who'd never been through an eclipse, so I was more conscious of my environment, and it got cold. It was really interesting. Okay. We know dust is an effective photon blocker. So the question that we began to ask was, what is its potential for solar radiation management? I just have this little sort of, fact that the Milky Way, you can see here in this image, has a vein of dust. And remember that dust is a very, very small part of the mass budget of the Milky Way, certainly compared to the stars behind it. It has high potential for modifying starlight. Okay, so we did calculations for how we might use dust to reduce the amount of energy here on Earth toward giving us a way of slowing or pausing better the increased sort of accelerating climate change that we're experiencing. So our calculation had kind of several components. First, we had to look for the right stuff. We needed to know how much we needed of that stuff to have an Earth climate impact. We also needed to identify orbits that would make it effective for blocking starlight. And finally, I'm way out of depth on this one, figuring out how to get to where it needs to be. It's more of a technical idea that we have to launch dust to put it into an effective Earth shield, sun shielding, solar shield orbit. So this slide just shows us some of our calculations. And I kind of bring it up here. It's Yeah, we really did look at coal dust as one of the material that we could, four types of material that we could use to block sunlight. And that seems kind of ironic because there's a, if you want to dig coal dust out of the ground, why not ship it to L1? So this just is a slide to illustrate that we looked at various compositions and various configurations of dust, fluffy, possibly even needle-like, and so this slide just illustrates that we were able to estimate the amount of material that we need to attenuate sunlight at a level that would help us mitigate climate change. Figuring out where to put the dust is straightforward. Keeping it there is a bigger issue, but we did consider how effective dust is at shadowing Earth. You have to have dust in place between Earth and Sun. You can imagine that if you put the dust too close to the sun, it's not going to provide any shade whatsoever. But there's a sort of a window where you can put locate your dust that allows the shadowing of the Earth nicely. And the L1 point turns out to be very close to the optimal distance. Okay. The other issue that we had to consider when we're looking at orbits is the persistence of dust particles. If we put them at L1, I mentioned that radiation pressure is going to work against you. It will move that dust away from L1. So we explored other places where perhaps the radiation pressure and Earth's gravity would conspire to keep dust in mind, but that unfortunately requires the dust to be too far away to be an effective sun shield. But these kinds of calculations were part of our work. So I put up this plot for you that shows the disk of the sun and the location of something in orbit at the L1 point for Earth. This location, this object is persistent for some time. I ran this simulation for a year, and it just dances back and forth. And the dance back and forth is the result of one thing. It's the moon. And we're part of a nice system with our partner almost mini planet. So this simulation really illustrates the challenge. If your faculty meetings do get out of hand, they get way off the rails, I encourage you just to watch the simulation. It's very peaceful. And it shows the effect of radiation pressure on dust that's being launched from a platform that follows the path I showed in the last slide. Okay, it doesn't persist, but it will, when at least while it's in place, will be an effective solar shield. This was an idea that we came up with as our project evolved, that maybe it wasn't worth trying to keep dust at L1, but maybe it would be a fun idea to consider some other orbit between Earth and Sun that would allow the dust, despite the forces that it feels, to track the path between Earth and Sun. And this, I think, is our favorite strategy. So the delivery, I'm not going to spend much time on. I am way out of depth on this, except to note the third point here. If we want to put dust between Earth and Sun, if we want to launch it on a path that effectively blocks sunlight at the level of having an Earth climate impact, then launching from the moon is a lot easier than launching from Earth. Of course, you have to set up shop there, but nonetheless, the energetics, once you do, the energetics favors a lunar origin. So here's a possible scenario. We've got lunar dust. The size distribution of the regolith is really good for per unit mass for blocking sunlight. The regolith is meters deep. It's kind of a ready-made supply of material. A moon launch requires less energy than Earth launch. You can envision platforms that could be assembled, perhaps solar powered, with modest excavation efforts. And we're talking about an amount of material that's the scale of local Rio Tinto operation. So you could excavate, simply move the regolith to electromagnetic launchers. After we published, we saw some really interesting and innovative ways of doing this. The nice thing is that you have a solar shield, but only when it's on. The dust doesn't stay for very long. You launch it, put it in place, eventually it's going to get blown out. So the dust is dispersed in weeks. The dust disperses into the solar system and not Earth. And I get to say that because I did test that. And it's all where it went. It didn't land back on us. Okay, so here's my assessment of this, this strategy here. We have a dust shield, it's feasible. The orbit choice is key, factoring in the non-gravitational forces of radiation pressure. Lunar dust on an Earth-Sun intercepting orbit, the ESI that we have there, or an L1 station where dust is launched could be favored from an energetic perspective. Advantages to the strategy. This strategy has far less direct environmental impact if you don't consider what's required to set up on the moon for this process. It has far less direct environmental impact compared to, say, launching aerosols into Earth's atmosphere. Dust is blown beyond Earth, it won't rain down upon us. It does require constant replenishment. We can stop in days, we can control what we do in terms of the sunlight that reaches the Earth. That's an important point, I think. This was also a disadvantage because we constantly need to replenish the dust, and so this leads to a potential failure mode of maintaining the solar shield in this way. This will definitely require international cooperation, and it will definitely be expensive. But compared to what? After the work that I just described kind of got out there, other people have kind of considered this idea, and I'm going to focus on, well, just these two. The one on the left, some folks have identified another orbit around L1 that may have better persistence than ours. The one on the the lower right here is an idea that originated with Dan Fabricki at the University of Chicago, and I've since joined on with him to work on this project. I'll just say a few words about that. This is our artificial planetary tori collaboration. We were going to go with just the pets in the image, but we didn't. This is Ashley Maglino, a graduate student here at the University of Utah. I'm working on this project. That's for Cat Farr. These are the right puppies, Wilbur and Oral. So these are graphics from this work where we're launching dust in orbit around bodies. The upper left just shows rings of dust around Earth. The upper right is something I'll mention in the next slide. When you put a ring of particles or satellites on Earth, they would naturally, at some level, tend to sort of stay in a fixed angular momentum. And as the Earth moved around the sun, their orientation relative to the sunlit side of the Earth would change. This is a sun-synchronous orbit where the oblateness of the Earth changes gravity enough to keep the dust in line with the sun-facing side of Earth. So this is a picture of the Earth as seen from the sun over the course of a year, and that ring of particles sort of stays illuminated by the sun, casting a shadow on Earth. You can ask me about the other two plots if you want. They're fun. So this is what a sun-synchronous orbit might look like. The precession that this ring of particles around the Earth would experience fixes the alignment between Earth and Sun as the orbit. So if this were set up so that in such a way that this shadow fell at noon locally as the Earth spun, then you could have, you'd be guaranteed to have a shadow that helps cool Earth. The complications for this scenario include radiation pressure, as mentioned, atmospheric drag, because we're getting close to the surface of the Earth. Possibly a kicker will be photoionization of dust particles having electrons kicked off and they become charged and then interact with the Earth's magnetic field. All these effects are taken into account in actually magneto simulations. We have a bit to do before giving more seriousness to this idea, but imagine what this looks like. You've got a ring of particles that we see every day at noon. If that ring were dense enough, we would eclipse, or we would be in an eclipse zone for approximately 10 minutes in order to achieve the kind of Earth cooling that we would want. So that would be our day. That would become our world. We go about our business. At noon, we have our jackets. I think it's amazing. Okay, there are pros and cons again for this idea. Certainly, the one I want to focus on is deployment may be easy, but we are introducing a whole new suite of hazards. This material is not going away. It's not going to scatter off into the solar system. It will return to our planet. It will pose a serious environmental impact, potentially, depending on what the dust is made of, and certainly a space hazard. Okay, but it's Earth, right? So we can do without communication satellites for 30 years. So to summarize what I talked about today, dust as a solar shield is challenging, but turns out feasible. We have proposed certain orbits. We're working on others. This, I must emphasize, to the point, cool story then, is a short-term strategy. Years to implement, possibly a decade, but not decades. The duration would be decades, not centuries. This is not a solution to the climate change problem here on our Earth. The environmental impact could be made low, potentially, or zero if you adopt our lunar dust strategy. And again, the intent is a fail-safe mechanism to buy time, to complete the real work that we're doing, underscored by the very existence of the Wilkes Center for Climate Science and Policy. So I have one question for you as I leave this talk. Is this a good idea? Thank you all so much.
I wanted to ask if the Society of Physics students, do you have representatives from SPS? Hoping that someone will do it, because I promised to give them the first question. How about any students?
Yeah, please. With regards to, I thought it was a really interesting idea.
Thank you.
Never heard of this before. I think it's really cool. I do have, I come from a space background, and so I'm aware that there's a lot of satellites in orbit. And even at the run from we have satellites that like towards the sun and do solar research. How does like the dust impact both scenarios?
In both scenarios, dust is an unambiguous space hazard. We have worry about it. It actually turns out that our plan of launching dust toward the moon on an Earth-Sun intersecting orbit wouldn't bother anyone, because that dust actually never reaches L1 proper. It gets deflected beforehand. So if you really wanted to preserve communication satellites, the scientific experiments that exist, solar observations often at L1, you might choose that strategy. When we began floating the sun's synchronous orbit, it was done so at a telecon at NASA Goddard, and you could feel over the internet the uncomfortableness of the idea of launching billions of kilograms of dust into that orbit. So yeah, thank you.
Opening up for anyone to ask questions.
Hey, how did you get into studying the dust in general? Like, what made you choose dust instead of like maybe the other ideas in general?
That's a great question. In the progression of my work to understand planet formation, I started roughly in the late 90s. I'm working with a collaborator, Scott Kenyon, and we ran simulations of how planets grow. At that time, there were very few exoplanets known. But at that time, there were important indicators of exoplanets. And those indicators are the presence of dust rings as described. So that was our into planet formation, was studying the dust. And we just that became kind of our niche. And I still like planets, but dust is cool as well. Hey.
So I'm curious, and maybe this is not a question for you, but for other people in the earth science, but I'm curious in both scenarios, like what is the actual impact for the climate? Like, let's say you launch the dust, right, for 2 weeks period. Does that really, does that actually impact the climate, and does it cool down Earth by a certain amount?
This is a great question, and one of the reasons why I really liked the space dust at this level, less so the artificial planetary torus idea, was that if we were to do it well, put dust at L1, the effect of that on Earth would be more or less general reduction of the solar irradiance, impacting the entirety of Earth. That feels like a more neutral way of affecting the amount of energy and rebalancing the temperature here on our planet. And I also feel from a computational perspective, what that means for climate modelers is they change a single number. I don't know if that's true. But
I have sort of a similar question because a lot of the geoengineering solutions, there's concerns about unequal impacts, different parts of it. Am I correct in saying, if you put it at L1, it's sort of global. You're not seeing kind of latitudinal things.
that's
Even with those fluctuations.
That's right. I think,
Yeah.
yes, because the dust disperses so much.
So far
Yeah.
away.
And exactly right. The photons received are deflected globally from the planet. That's right. And that to me felt better. But every decision is a decision. That's why I'm really glad to be here.
Yeah, I think Derek is.
Yeah, so I'm just thinking of this from an atmospheric scientist kind of perspective with the sun synchronous kind of orbit. So we actually might have an analog of how that actually might impact the weather short term. So an eclipse would actually be kind of an analog to that. And what we actually saw with the eclipse, I think it was a couple of years ago now, was that when the eclipse is like moving over, let's say the CONUS US, what we saw is we see a suppression of convection. Convection would actually start to suppress. But that could be a little bit problematic, especially in tropics, which rely on precipitation from those storms. So I'm wondering if, has anyone run like simulations of like, I don't know, a climate model that probably has to be downscaled to some degree to kind of capture those impacts?
As far as we know, no one has considered the sun synchronous orbits that we've described. The one thing that I did want to mention about them is that little scenario, which is kind of sort of dreamy to me, that we'd have a 10-minute eclipse every day. That is highly unlikely given the physics of the dust motion. So we're much more likely to have a broad umbrella where you wouldn't have, it would be more of a global dimming, probably more analogous to cloud cover than as a single wonk. Although that would be really cool. Maybe we could do it sometime. As a celebration of this not great idea. Yeah, Angel.
So the sun synchronous orbit is a polar orbit,
It's almost always.
highly inclined. So do we need to worry about like the Kozai effect? What's the time scale? Maybe a decade we don't need to worry about that.
As far as I know, we don't have to worry about that yet on the timescales that.
So what's the altitude of this?
The altitude is like 1.2 or 3 I.
What's the unit?
Well, the altitude would be 0.2 or 3 I. So
Okay.
20% of the radius of the Earth above the surface. So,
Oh, okay.
so
And,
we'll be very close to the Earth, but we're dealing with more fierce problems with radiation pressure and the Earth's magnetic field. The charging is pretty extreme. We're likely having to go to more massive particles, in which case we'll need to deal with more classical orbits like you described because of that.
So any implications on the ground-based infrared astronomy?
I'm really glad you brought it up. Yes, this is you can imagine what this would look like if you spread dust diffused over the entirety of Earth. The one thing that I really like about this idea of keeping the dust particles low is that atmospheric interactions will bring everybody home on a time scale that's workable, so that we can add and subtract dust, maybe confining orbital configurations for a period of time. But yeah, that's Dan Fabricki is very concerned about this as well, to his credit, from the beginning of this project. So yeah, thank you. Yes.
It's a very interesting talk. You mentioned the charging issue and the ionization of the dust in the upper atmosphere, or above the atmosphere. And you mentioned that you had done some modeling work to consider that. And I wondered if that modeling work also considers the impact of that ionization on atmospheric chemistry and particle formation in the atmosphere. And if,
yeah, that's a great question. So we're pretty far out there. We're 1,200 kilometers, is that right? No, 12,000 kilometers out at, I gotta get that, sorry.
No.
We're at 9,000, a little less.
You said 0.2.
0.2, so I was correct. Sorry, not. So 1,200 kilometers above the surface of Earth. We're probably not in the significant atmosphere at that point. The charging is from photoionization, and once we sort of enter the Earth's atmosphere, we're probably in for other effects as well, just because the relative speed will be pretty high. So I'm not doing a good job of answering your question, but
I have to think about it.
I was kind of wondering something similar. It's when the particles re-enter the atmosphere that this will happen, right? I mean, if you're at this low Earth orbit, it's not stable. They're eventually going to get dragged back in.
yes.
And as you have this huge flow of material being dumped in our atmosphere, I imagine that's a much higher rate than we see typically from meteorites or anything.
I think that's right.
I mean, have you looked at that mass rate?
No, we have.
And then what would it do for particle formation, cloud formation? Or even if they're harmless particles.
Yeah. So we're at the level of this is basically from work that was just done. So we're at the level of seeing how we can keep particles at the the 0.2 Earth radii above the surface. That we're not having to deal with much atmosphere there. The magnetic field of Earth, we can actually push the sun synchronous orbits beyond that up to 0.5. So we can kind of reduce these effects, but keep them there. If they're large enough, they're going to stay there. The biggest problem that we have with them is the radiation pressure, which will push them around and then drive them on eccentric orbits into the atmosphere. And
Is there zero atmospheric drag out there?
there's not zero,
Not
but
zero,
it's
that would be
small.
I thought that would put in eventually.
It will eventually, but the timescales that we're looking at, which are basically years, so
Much
far
longer, the atmospheric drag is longer time scale.
out at that distance, yes.
Okay, that's why I was.
If we're not careful though, like if we build the stuff so it's really stable, say use 20 micron grains, which are much less susceptible to radiation pressure, do we really want to keep this stuff out there? I don't think we do. How are you going to get it down? Once we kind of figure out what we're doing here on Earth, decommissioning is a huge problem. Unless you keep particles kind of closer, but then we have these other effects. The atmospheric chemistry is well beyond what we know how to do, and would be really interested to know the impact. Again, what is the effect of dumping 10 billion kilograms of dust over the course of a year into the Earth's atmosphere? That could be Sorry.
They said nuclear winter.
Oh, okay.
Yeah. That's what it is.
Good
They
enough.
modeled that.
Good to know.
So 1,200 to like 3,000 kilometers, that's in the band elements, right? If so, wouldn't that mean that if they get charged, they'd be more likely to follow like the respective field rules, like how the war is formed?
That's likely there. We're doing those simulations now to know. Right now, what we're seeing, the size of particles that we're using and the level of charging we're assuming is simply from polarization. So 20 micron radius, the perturbation is relative. So we're not seeing, all of a sudden things spiraling tightly around field lines at this level. So it's mostly very, very perturbative.
Okay, I was curious if like the effects of the electric field would have electromagnetic field would have a stronger impact on that sort of thing.
That's right, yeah. Yes. Just one more reason why our northern neighbors read this stuff.
Last question.
Is there anyone out there doing like cost modeling or like logistic modeling for like, how do you make these things actually happen and how much would it cost?
For the lunar dust scenario, I have seen numbers, and it's not trillions of dollars, it's less.
Okay, well, please join me in thanks for